9.2, two variable linear systems. The other day we did 9.1. We talked about solving systems, both linear and nonlinear. We talked about solving systems by using two different methods. They were, what two methods did we talk about in 9.1 to solve a system? Substitution and graphing. Okay, so today we're going to talk about solving them by using elimination. So we're going to solve systems of linear equations. Notice we are going to stick with linear equations when doing elimination. We're not going to do a linear and a quadratic or anything like that. We're sticking with linear. We'll look at word problems. Yeah, we'll look at graphs. We'll talk about what it means, how many solutions, what they mean, that kind of thing. So here is a system of equations, and we want to solve a system by elimination. So if you recall in elimination, the idea is to, in fact, eliminate, hence the name, one of the variables. So if I had equations 3x plus 5, 7 equals 7, and negative 3x minus 2y equals negative 1, we could actually combine those equations exactly like they are, and the x's go away, right? X's have been eliminated. By eliminating the x, I have a very simple equation, 3y equals 6, which means y equals 2. And what do you do with that 2? Into what equation? Either one. Okay. And to use books terminology, they say that's a back substitute. So we figured out that y is 2. We're going to take that 2 and back substitute it into either equation 1 or equation 2. Does anybody have a preference for this problem? Why equation 1? Yeah. I mean, if I'm still trying to solve for x, equation 2 has a negative coefficient in front of x. So I would probably choose to plug that 2 into the equation number 1 to solve for x. Easy stuff? All right. So here it says by adding the two equations, you eliminate x, you get 2, back substitute it, off you go. Congratulations, you solved the problem. Okay, so the steps for eliminating. Step number 1, obtain coefficients on x or y. It doesn't matter what you eliminate, that are the same number with different signs. That way, when you combine them, it's going to go away. Step number 2, combine them to eliminate that variable. Step number 3, solve that equation. Step number 4, back substitute it into the original. And step number 5, very important, is to always check your answers. Always check your answers. That's step 4. He'll join us eventually, maybe. Okay, here's the system. We're going to solve it. By looking at this system of equations, which variable, in your opinion, would be the easiest to get rid of? Why is y easier to get rid of? We have a singular y. What else? Yeah, we already have one positive and one negative, right? So in order to eliminate the y's, what would we do? Multiply the second equation by 4. So I will take equation number 2 and multiply the entire thing by 4. So the first equation, I'll go ahead and write it down. We have 2x minus 4y equals negative 7. Multiplying equation number 2 by 4 gives us 20x plus 4y equals negative 4. And now the magic happens of elimination, right? We combine these two equations, and by combining them, that gives us how many x's? 22x. What happens to the y's? They've been eliminated. 22x equals negative 11. X is negative 1/2, right? Negative 11 divided by 22 reduces to 1/2. Negative 1/2. Now what? Okay. Yeah, we have two different things to look at here. X is -1/2, which means I'm going to take the coefficient and multiply it by 1/2. So if I plug it into the first one, that's kind of convenient because the coefficient on the X is an even number, and 1/2 of an even number is a nice number. And then you got to divide by -4 and all that other math. If you plug it into the second equation, we already have y by itself. So a person could argue on this problem, either way. I don't care. So how many of y'all want to plug it into the first equation? 3 of you. Second equation? 4 of you. So plug it into the second equation. We have 5 times x, but x is -1/2, plus y equals -1. -1/2 of 5 is -5/2, plus y equals -1. Add 5/2 to both sides gives us make up our minds. 3/2. So what is the solution to our system? -1/2, 3/2. And of course, the next logical step would be go ahead and plug it in and make sure, right? Okay. I'm going to assume that y'all know how to do that. I don't want to spend time on that process. These are nice fractions and they're nice decimals too. It doesn't really matter, I don't think. Yeah. Probably a fraction. Yeah. Yeah. Okay, so here they are. They're showing they got the answers. They're showing that they plugged it in. They get a true statement. So the solution is in fact correct. -1/2, 3/2. And checking the equations. There's the check into equation 1 and equation 2. It makes both equations true. Therefore, we're good to go. In example 1, the two systems of linear equations, the original and the system obtained when we took that second equation and multiplied it by 4, right? Those are equivalent systems. Equation 1 stayed the same. Equation 2 was only different by a factor of 4. So those are called equivalent systems. They have the exact same solution set. Operations to be performed in a system of linear equations. We can interchange any two equations. Like if you're writing them down, if you want the first equation to become the second equation, you can do that. It doesn't matter. It doesn't matter the order of the equations. Number 2, you can multiply an equation by anything but 0. What happens if you multiply an equation by 0? Yeah, you eliminated everything. So good luck solving it because everything's gone. So don't multiply by 0. Number 3, add a multiple of one equation to another in the system. I like the fact that they say add. You'll never hear me say subtract. If I had a 3x and a 3x, I wouldn't say subtract the second equation from the first one. I would say multiply the second one by -1 and then combine them. Subtracting equations tends to just cause problems because you forget to take that negative sign and transfer it to every piece of it, okay? Okay, so when you solve a system of linear equations, there's 3 possible outcomes. The possibilities are the lines cross. If the lines cross, how many solutions are there? 1 solution. Another possibility, infinitely many solutions. What's that mean? Same line. Those lines rely on each other. They lie on top of each other. If that's the case, you have infinitely many solutions. And if they never touch, they're parallel, no solution, right? We have a couple of different words to talk about. We have consistent, inconsistent, dependent, and independent. If you tell me a system is inconsistent, you are telling me there's no solution. If you tell me it's inconsistent, you don't have to tell me anything else. Inconsistent, no solution. Okay. However, if you tell me a system is consistent, consistent means there is at least one solution. So at least one means there could be one or there could be more, right? And if we're talking about lines, more means infinitely many. There can't be two solutions to a line, can there? It's either one, none, or infinitely many. Okay, so consistent means there's at least one solution. What does independent mean? Forget math. What does independent mean? By itself. You do your own thing, right? So if I have two lines that are doing their own thing, they probably have different slopes. They're going to intersect. Okay, so consistent, independent, one solution. What does the word dependent mean? You rely on someone. Okay, so a dependent system, the lines rely on each other. So it's the same line. The lines lie on top of each other. Okay, questions about those definitions? Okay, at least one of you are going to get those definitions wrong on a test. Prove me wrong, please. You wrote them down? I don't care. Somebody will still miss it. So here are three systems, and it wants us to match each linear equation with the graph. We want to describe the number of solutions and state whether the system is consistent or inconsistent. Look at system A. What do you notice about those?
They lie on top of each other.
Do they? Are they the same? Is it?
I don't. Are we talking about one?
We're talking about A.
Wait. Oh, wait.
We're talking about A. Are they the same? The same would mean if I took one of them and multiplied it by a number, I'd get the other one. Is that true? How come? Okay, so we got an issue somewhere, right? So let's just say we took that first equation and multiplied it by 2. What does that give us? Okay, and what's going to happen if you combine those? 0 equals what? And how do you feel about that? Not true. That would be considered an inconsistent statement, right? Because they're not the same. What does inconsistent mean? How many solutions? No solution. Because they are, the lines are no solution, they are parallel, right? So this, okay, so which picture would that be? Okay, so I'm going to put an A right here. Say if they go together, okay. We have 0 solutions. And the system is inconsistent. Okay. Anything fancy about B? Are they the same? Can you multiply one by something and get the other? Okay, so what's that telling you? Huh? One solution, right? I can't make one look like the other. So consistent or inconsistent? Consistent. How many solutions does B have? So right here, we have one solution. And we have consistent And it doesn't ask us to say anything about dependency, but Sean is exactly right. This is independent, right? Lines are doing their own thing. Letter C, what do you notice? Okay, yeah, they're the same line, right? If you took that first one and multiplied it by -2, you'd get the second one. These are exactly the same lines. Or if you took the first one and multiplied it by 2, you would get 0 equals 0 if you combine them, right? Which is a true statement. So this is C. Is this consistent or inconsistent? Consistent. How many solutions? No. Infinitely many solutions. Consistent. Pretty simple so far. Here are the text descriptions of what we just talked about. You're welcome to capture that if you want and read it yourself later on. I'm moving on. Applications. At this point, you may be asking the question, how can I tell which application problems can be solved using a linear system of equations? Consider the following. Number one, does the problem include more than one unknown quantity? Number two, are there two or more equations or conditions to be satisfied? So more than one unknown, more than one equation. Because you only have one equation, is that a system? Is one equation a system? No, you got to have at least two, right? So as long as we have more than one unknown, two or more equations, then yes, we might be able to do it to solve this problem with a system. All right, so we have a situation. I'm going to leave it like it is. An airplane flying into a headwind is flying from Massachusetts to Utah. From Massachusetts to Utah, it takes 2 hours, 24 minutes to cover that 2,000-mile flight. The plane can fly back from Utah to Massachusetts, and it only takes 4 hours. We're going to assume that from the moment that plane takes off, it's going to fly at a constant rate. So it's got an instantaneous speed. And when it lands, it's going to land abruptly and go from that instantaneous speed to 0. We might have a slight case of whiplash among the crew and passengers. I don't know. Anyway, so here's the problem. I'm flying into the wind. I'm flying with the wind. We have two variables, don't we? We have plane speed. We have wind speed. Okay. So let's think about this. Let's define some variables. What do you want to use for variables? Okay. Let P equal plane speed. Let W equal wind speed. And I'm going to show you the next slides because when they work it out, they use R1 for one of the speeds and R2 for the other speed. Yeah, I would not do that. I wouldn't do X or Y either. I like meaningful variables. So if you're flying from Massachusetts to Utah, how long is the plane flying? 4 hours and 24 minutes. When you're flying from Massachusetts to Utah, how long is the wind blowing? 4 hours, 24 minutes. That's what they're telling us to do, right? We have a consistent speed on both the plane and the wind. If you're flying against the wind, is the wind going to help you or hinder you? Okay. So any thoughts on this equation? How do you calculate distance? In physics class, distance is equal to speed times time, right? So let's talk about the distance the plane goes. How far is the plane going to fly? Based on distance and time. How far is the plane going to fly based on distance and time? What numbers would you multiply together? Because you told me distance is, distance is times rate, correct? Okay. Talk to me about the distance the plane is going to fly. Are you multiplying by 2,000? How fast is the plane going? We don't know. What represents the speed of the plane? P. Okay. Okay. And this is kind of convenient. 4 hours and 24 minutes would be 4 hours and 24 minutes, right? And this is actually a nice decimal. What is 24 divided by 60? What is 24 divided by 60? 0.4. So this is actually 4.4. Okay, so we're going from Massachusetts to Utah. And yes, I'm ignoring the name of the city in Massachusetts. I'm okay with Salt Lake City. I guess Chicopee, I don't know. Okay, so here we go. Massachusetts to Utah. We have 4.4, that's the time, times the rate. That's how far the plane is going to go, correct? What are we going to do with the wind? Add it or subtract it? Because we're going against the wind, we will subtract. Now, how long is the wind going to blow? The whole time. How fast is the wind blowing? W. Once we combine the distance the plane flies and the distance the wind blows, how far will we travel? 2,000. How are we doing on this, guys? Y'all following? Okay, great. We're there. Now we're going to come back. And this wind is blowing nonstop for a very, very long time. But now we're going from Utah back to Massachusetts. How long is it going to take us? 4 hours. How fast is the plane going? What's the wind going to be doing? Helping us. So plus the same amount of time, the same amount of wind, and the distance. Okay. There you go. There's our system. I'm going to tell you right now, there is no way in the world I would ever solve this problem using elimination. I would not do it. But the problem is in the elimination section, so let's do it. Okay. The easiest way to get, well, first of all, the wind's going to be eliminated, right? One's positive, one's negative, be pretty easy. If we took the first equation and multiplied it by 4, and the second equation and multiplied it by 4.4, can you see that that would in fact eliminate the wind? Okay, so 4 times 4.4 is 17.6 P minus 17.6 W equals 8,000. Second equation, multiplying by 4.4, we have 17.6 P plus 17.6 W equals 8,800. Combine 17.6 give us 35.2 P. The wind is gone. 16,000 800. Divide both sides by 35.2. P is equal to, approximately equal to 477.27 miles per hour. And then using your calculator, use that answer, don't round it, use that answer and plug it into one of the originals to solve. And once you back substitute, you get the wind speed. And that's going to be on the next slide. I'm not going to mess with doing it. I'm going to assume that all of y'all can plug that in. Okay, questions? Okay, so let's go ahead and look through the book's example of how they solved it. Just, I told you they used R1 and R2s and all this stuff. But anyway, I'm just going to skip through this. If you want to take a picture of it, you can. I'm moving on. Next slide. I'm moving on. Again, I'm moving on. Oops. Okay, so they got 477.27 for the speed of the plane. Once they back substitute that, they get that the speed of the wind is 22.73 miles per hour. All right, questions? Okay, so 9-1 and 9-2 are due Monday midnight. Okay, and there you go. And we'll start into 10-1 on Monday. Tuesday. Squimpus, any questions?